At first light, Devil's Tower does not look like a mountain. It looks cut. The walls rise in vertical bands so regular they resemble grain in petrified wood, and the summit sits flat enough to feel less like a peak than a surface left behind. In old photographs, before the roads and guardrails and visitor maps, it stands alone above the plains like a severed thing. Not broken by chance. Not softened by time. Just there, immense and exposed, with the proportions of an object too large for the landscape around it. The familiar explanation calls it an igneous intrusion, a body of magma that cooled underground and was later revealed by erosion. That is the official explanation. But when a mountain begins to look less like uplift and more like a stump, the eye does not easily forget it. The accepted timeline is straightforward. Over millions of years, molten rock forced its way upward into older sedimentary layers. It cooled slowly, forming long columns as it contracted. Then wind, rain, frost, rivers, and deep time removed the softer material around it, leaving the harder core standing above the land. Geology has a language for each stage. Laccolith, plug, columnar jointing, differential erosion. The labels are tidy, and many of the measurements do fit. Similar structures exist elsewhere. Basalt can fracture into columns. Volcanic necks do survive after the cone is gone. By the time the story reaches a textbook, everything is settled. The structure is ancient. The process is known. The case is closed. And yet there is a problem. The official explanation often describes forms, but it does not always explain why certain forms feel so specific. There are mesas whose rims resemble bark torn away in great sheets. There are buttes with fluted sides and broad, level crowns. There are isolated stone masses ringed by talus like rotted fiber collapsed from a harder core. There are mountains with radial ridges that resemble root flare more than drainage. There are landscapes where the scale is wrong in a particular direction, as if something organic had been enlarged beyond any accepted biological limit and then translated into stone. Once that resemblance is noticed, it begins to repeat. And the repetition is difficult to ignore. So the theory is not that every mountain is a tree, or that geology is a fraud, or that the earth has no history. The theory is narrower, stranger, and more serious than that. It suggests that a small class of isolated mountains, plateaus, and column stone formations may be the lithified remains of a forest so ancient, and so unlike the biological world now known, that it was reclassified as geology before it was ever seriously tested as anything else. Not a fantasy forest from myth, but a physical one. Towering life on a scale that modern categories no longer permit. Something cut, buried, mineralized, eroded, and finally renamed. The stone remembers. What changed was the explanation. Begin with form, because form is what first disturbs the record. Devil's Tower is not merely vertical. It is striated in a way that evokes bundled fibers. The columns are often described as hexagonal cooling fractures, and that is fair, but the total geometry still presents a question. The overall body narrows slightly, rises cleanly from a wider base, and ends in a flattened top as if the upper mass had been removed. The nearby landscape does not rise into it gradually. It does not behave like a range. It behaves like an isolated object embedded in terrain that seems unrelated to its shape. The same visual tension appears at Bear Lodge, at Shiprock, at certain table mountains in Africa and South America, and in many smaller formations catalogued within different names. Tower, butte, knob, plug. The words describe what is seen from a distance. They do not settle what is being seen. The record shows repetition before it shows explanation. Then there are the crowns. Across several continents, flat-topped mountains are treated as ordinary products of resistant caprock and erosion. In many cases they are. But not all flat tops are equal. Some do not look weathered down so much as cut off. Their upper surfaces appear abrupt, level, and curiously detached from the slopes below, as if the landscape had preserved a cross-section rather than a summit. In ordinary mountain building, one expects ridgelines, fractures, accumulated debris, chains, systems. But some of these masses stand apart with a geometry closer to truncation than uplift. The question is not whether erosion can flatten stone. Of course it can. The question is why erosion in so many scattered cases leaves forms that resemble severed columns with radial texture, root-like buttressing, and surface patterns more legible as once living structure than as accident. That is where the official explanation begins to feel incomplete. Old photographs deepen the unease. 19th-century survey images from the American West, from southern Africa, from Australia, and from parts of South America repeatedly present landscapes dotted with enormous stumps of stone standing above comparatively immature tree cover. In many of these photographs, the surrounding forests look small, young, almost secondary, as though whatever larger world preceded them was already gone. There is a silence in those images. Surveyors often recorded scale carefully, but not speculation. A tower is named a tower. A butte becomes a butte. A mesa is entered on a map. Classification replaces curiosity. Yet the eye still notices the same arrangement again and again. Isolated cylindrical or flared masses, flattened crowns, surrounding debris slopes, and adjacent strata that resemble chips, splinters, or peeled layers. The record is still there. It is not proof by itself. But it is the beginning of a pattern. Measurements make the pattern harder to dismiss. Consider the ratio of height to diameter in certain formations, and the way some widen at the base in apparent structural support, much like buttress roots scaled into geology. Consider the vertical grooves that run uninterrupted for hundreds of feet, not as random weathering, but as repeated parallel architecture. Consider the concentric or semi-radial fracturing visible from aerial surveys around some isolated peaks, where drainage and slope failure follow lines that look strangely like growth geometry. Standard geology can account for many of these traits individually. Cooling columns, joint sets, exfoliation, erosional remnants. But a system of explanations applied piece by piece is not the same as a single explanation that feels proportionate to the total form. What matters is accumulation. A column can be volcanic. A flat top can be erosional. A radial base can be structural. But when these traits converge in the same objects across large distances, the question sharpens. To be fair, mainstream geology does address the resemblance. Geologists are not blind to morphology, and many have noted that human perception is easily tempted by analogy. We see faces in clouds, animals in coastlines, architecture in crystals. Columnar jointing is a real, documented process. Basalt and phonolite can crack into strikingly regular polygons. Volcanic plugs and necks do remain after surrounding material wears away. This is the strongest counterargument, and it deserves to be stated plainly. The hidden history theory becomes worthless if it ignores known rock processes. But this fair explanation still leaves open several things it does not fully test. It does not usually ask whether some formations that have been visually grouped as volcanic were ever examined through the lens of fossilized biological macrostructure. It does not ask whether mineral replacement could preserve former tissue architecture at scales no modern botany expects. It assumes category first, then evidence inside the category. That is not fraud. It is habit. And habit can hide a great deal. Scale is the first objection most people raise. Trees do not grow into mountains. Not now. Not in any forest on Earth. Known biology has limits of water transport, structural loading, atmosphere, and metabolism. That is true. But those limits belong to present conditions and known lineages. Paleobotany already records worlds that would seem absurd without fossils to force belief. Giant club mosses the height of houses, dragonflies with vast wingspans, swamp forests unlike any living biome. The Carboniferous was not invented to flatter imagination. It was reconstructed from remains. If the deep past supported organisms that modern ecosystems cannot, then scale alone is not a rebuttal. It is a boundary condition. The real question is whether there are mineralized forms on Earth so large that science ceased considering them biological before the comparison could be made. The pattern does not disappear simply because the scale is offensive to current intuition. The landscape around these formations also deserves attention. In a conventional erosion model, debris accumulates according to rock hardness, slope angle, jointing, and climate. But in some locations, what surrounds the central mass resembles not uniform collapse but layered shedding, like giant bark plates, splintered wedges, and fibrous talus. Again, analogy is not proof. Yet there is a recurring visual grammar in the ground. On some mesas the outer layers peel in broad sheets. On some isolated towers the base is ringed with long angular fragments that look less like random rubble than like longitudinal breakage. In satellite imagery, certain terrains show radiating gullies and fan patterns that resemble the spread one might expect if a rooted structure once directed stress and runoff outward from a central trunk. Geology has names for all of this. Scree, joint blocks, exfoliation slabs, drainage fans. The naming is not the issue. The issue is whether naming stopped further comparison. What remains is a landscape that keeps whispering the same shape. Then widen the scale. Do not stay with Devil's Tower. Look at the tepuis of Venezuela and Guyana, the stone pillars of Madagascar, the flat-topped tablelands of southern Africa, the columned towers of the American West, the isolated monoliths of Australia, the cut-looking mesas of the Arabian deserts, the stump-like peaks scattered through Central Asia. These are not one formation in one province with one local explanation. The pattern repeats across continents. Some are sedimentary, some volcanic, some metamorphic, some disputed. That variety is often used to dismiss any common reading. But it can also suggest something else, that different mineral environments may have preserved different parts of a former biological reality in different ways. Wood does not always fossilize into one texture. Tissue mineralizes according to chemistry, pressure, burial, fluid movement, and time. If an ancient macroforest existed far enough back, under conditions no longer present, one would not expect uniformity. One would expect fragments. Stumps here, casts there, root fields elsewhere. The pattern repeats, even when the labels do not. There is another layer to this, and it is institutional rather than geological. Truth is not always hidden by a villain. Sometimes it is hidden by file cabinets, department boundaries, budget cycles, and the inertia of accepted categories. A mountain is studied by geologists. Fossil wood is studied by paleobotanists. Large-scale landform classification belongs to mapping agencies. Each field inherits methods designed around a certain scale and a certain prior belief. No one commits a crime. No one needs to falsify a report. The possibility simply fails to fit the boxes through which evidence is processed. Samples are taken from the rock, not from the form. Papers focus on mineral composition, age dates, cooling histories, and regional context. All useful, all real. But if the wrong question is asked with perfect rigor, the result is still a blind spot. Classification can bury a thing more effectively than secrecy. Bureaucracy leaves fewer fingerprints than conspiracy. The historical timing matters as well. Many of these formations entered formal scientific description during periods when the earth sciences were consolidating authority through standardization. Naming, mapping, sectional analysis, and stratigraphic order brought coherence to a previously chaotic field. That achievement was immense. But every new discipline stabilizes itself by reducing anomalies, not multiplying them. Ambiguous forms are absorbed into the nearest durable category. The process is understandable. It is also consequential. Once a formation is entered as volcanic, erosional, or sedimentary in the literature, later observers inherit the conclusion before revisiting the premises. Guidebooks repeat it. Museums teach it. Tourism packages it. School children memorize it. The object itself does not change. Only the permitted questions do. What changed was the explanation. There are also curious absences in the record. If certain isolated monoliths are the exposed cores of volcanic systems, where are the broader volcanic signatures one might expect in some cases? Extensive lava fields, crater structures, consistent surrounding deposits, associated feeder systems that are not merely inferred but clearly preserved? Sometimes they exist. Sometimes they are plausible but partial. Sometimes the surrounding terrain looks oddly detached from the violence required by the explanation. A plug without a cone can happen. A remnant without its context can survive. But repetition matters here too. How many singular geologic events can a landscape contain before singularity itself becomes a pattern? There is a difference between an object that can be explained and an object that has been explained enough. The hidden theory begins in that narrow space between possibility and sufficiency. Even language may preserve an older intuition. Across many cultures, prominent stone formations are described in terms of giants, petrified beings, sacred poles, world trees, severed columns, and places where the land was cut. Myth is not data in the modern sense, but it is often a record of how forms were perceived before technical classification replaced local description. Indigenous traditions surrounding certain monoliths frequently treat them not as ordinary mountains but as transformed remnants of a different order. That should not be exploited carelessly, and it should never be stripped from its original context. But it can tell us something important. Long before geology named these places, people already sensed that they were not quite like the mountains around them. The first witness was the eye. The second was story. Only later came the report. If the theory is wrong, it should be wrong under examination, not ridicule. That is the point that matters most. There are ways to test parts of this seriously. Comparative morphology across global monoliths. Microstructural analysis targeted not only at mineral identity but at patterned organization. Broader surveys of radial landscape geometry around isolated formations. Reassessment of specific volcanic towers where surrounding evidence is weak or inferred. Even a negative result would be useful. It would tell us that resemblance here is only resemblance. But dismissal without directed investigation is not science at its strongest. It is consensus guarding its borders. The record is still there. The stone remains in plain sight. The photographs remain. The maps remain. What is missing is not material. What is missing is permission. And that is why the idea refuses to die. Not because it is sensational, but because certain places on Earth continue to feel mislabeled. A person can stand beneath one of these monoliths, touch the vertical bands, study the flat crown, walk the ring of broken stone at the base, and sense that the official explanation is complete in one register and strangely thin in another. This is not about rejecting geology. It is about whether geology, like every mature system of knowledge, may have inherited a small number of objects that it describes accurately in composition but incompletely in origin. There is a difference. A fossil is still stone. A stump, mineralized long enough, is still rock. The categories do not cancel each other. They overlap. So the unsettling possibility is not that mountains are secretly trees in any simple or childish sense. It is that a few of the most isolated, columned, flat-crowned stone giants on Earth may be the last readable remains of a biological world so old, so transformed, and so far outside current expectations that it passed into the geological record under another name. The forests disappeared. The chemistry changed. The burial was deep. The scale offended belief. Then erosion unveiled the cores, and later institutions assigned them to the nearest familiar process. The pattern does not disappear. It only becomes harder to say aloud. When that happens often enough, a civilization stops seeing anomalies and starts seeing scenery. A severed tower becomes a landmark. A stone stump becomes a hiking destination. A cross-section becomes a summit. Children are told they are looking at mountains, and in most cases they are. But there may be a handful of exceptions so large that the mind protects itself by refusing the comparison. That is how forbidden patterns survive. Not under lock and key, but in plain sight, covered by the confidence of ordinary explanation. The real question is not whether the theory sounds strange, but whether anyone with the tools to verify it has seriously looked.